wanted to look briefly at closed systems. Most often we're looking at open systems in combustion problems, but sometimes they're closed systems. And example, so if I look at closed systems, example 1210, page 393. So you should look and see what that problem is, but basically we're going to have a closed system. We're going to have in here methane and oxygen, and it's a 298. We're going to have combustion occur, and it's going to end up that I'm going to have the products at 400 K. So, and obviously there's going to be heat flow from this. And so when I look at this, if I do a first law analysis, I'm going to have Q plus Q is equal to delta U plus W. There's no work done. So this is equal to U2 minus U1, which would be equal to the internal energy of the products minus the internal energy of the reactants. And you notice that heretofore everything is dealing with enthalpies, so we have to go back and modify the equations so that it includes the internal, so it can be used for internal energy. And this goes, U bar is equal to H bar minus R bar T for gases. So when I look at this, this is U is equal to H plus PV, minus PV is equal to H minus RT. And so we had dealt with this earlier in chapter 3, and now we have it back and we're writing it on a mole basis. So what we have to do for the enthalpy terms in the reactants and products is include a minus R bar T term. So the internal energy of the reactants is the sum of the Ni times our H sub F bar 0 plus our delta H minus R bar T. And the internal energy of the product, this is reactants, the product, and J times H sub F bar 0 plus delta H minus R bar T. And so this will be at 298, this is at 400. And then you solve for Q. And so the example goes through solving for Q, and there are a number of math steps that are not typically fun to watch going through, so you can read them. But this is the concept. So I wanted to talk about the concept is that I need internal energy. All the tables and information is presented as enthalpy. I have to convert and find the internal energy knowing the enthalpy for gases with this equation here. So for homework, do 1229, 1233, 1247, 1248, 1265. And now what we want to introduce is a topic, how hot is hot? And so what we have, how hot is a flame? So if I have a flame, what is its temperature? What is the maximum temperature I can get from burning methane, from burning propane, from burning octane? So what is the maximum temperature that we can have? And that's called the adiabatic flame temperature. So the adiabatic flame temperature and what this does is it tells us what is the maximum temperature we can get from a combustion process. And so if I look at the first law analysis and I do Q plus HR is equal to W plus HP, The maximum value I can get is if it's adiabatic, no heat, and no work is done, so I have HR is equal to HP. And so what I want to do is to be able to find that. This will become a trial and error process. And we have example 1211 to look at. And so in 1211, we're going to look at propane at 100% and 400% theoretical error. So you may want to look at that. What we see, what you might see right away, is if you remember, if I'm burning with air, there's that nitrogen that gets carried along. I have to heat the nitrogen up in the products. So the less nitrogen I have to heat up or raise in temperature, the more energy can go into increasing the temperature of the product. If I have more nitrogen, then the temperature is going to go down. So we can regulate the temperature of the combustion process by the excess air that we have because of its heating up, raising the temperature of the nitrogen. So if we balance the equation as is in the text, so we have propane C3H8 plus 5 times O2 plus 3.76 N2 yields 3 CO2 plus 4 H2O plus 18.8 N2. And so this is for 100%. So you should be able to balance these fairly quickly. And we're going to start off that the products are 298. So H sub R is equal to H sub F bar 0 of the propane C3H8. And this is equal to minus 103,909. Table C1. So we do that. And now let's do the enthalpy of the products to make a little more space. H sub P is 3 times minus 393,757 plus delta H. Leave a little space in your notes above here. This is for the CO2 plus 4 times H sub F bar 0 minus 241,971 plus delta H for the H2O plus 18.8 times delta H of the N2. So we don't know what those values are. But if I look at this number, so if I look at these numbers, and I multiply 3 times this, I have minus 1,181,271. If I multiply 4 times this, I have minus 967,884. And here I go. So if I add these two negatives together, I have minus 2,149,155. So, and what I need, so the products, if the products right now, HP, without any delta H term is going to be this, and I want it to balance this number. So the only way I can have it balance this number is these delta H's have to be big enough. These are all positive. So this is a positive number, positive, positive. So they have to be big enough to drive down this temperature, this number, so it's equal to that minus. So we need to drive down those values. And so what happens is that I'll guess T sub P is equal to 2,500. If I put in all the delta H's for that, I'll get that H sub P is equal to plus 10,845. And now what I want to do, so there's a graphical way to help us do this. So I don't have it quite balanced, and what happened is this was too high a number, so I ended up with a positive number. Rather than having it be minus 103,909, I had it positive. So now, how do we do this? So you can use linear regression on your calculator and write a program for it, but for our purposes in this course, it's fairly easy to just do it, have an idea how to do it graphically. So if I plot something, so if I have here HP minus HR is 0. So here I have 0, and now I'm going to have, let's say, plus 100K minus 100K. Anyway, we set up the tables, and then I have various temperatures. 1, 2, 3, 4. So I have 1,000, 2,000, etc. And so what I'm going to do now is, if I subtract this HP minus HR, we're going to be up here for this one. So that's the first guess. So it'll be around there. And so now what, a little bit less than that. And so now what we're going to do is we guessed TP is equal to 2,300 degrees K. And we get that H sub P is equal to minus 206,068. So we overshot the mark. So now on this guess, I'm going to be down here somewhere. And what we do is we say draw a straight line, look at where it intersects, and this gives you your adiabatic flame temperature. And you could iterate this more. So in this case, the adiabatic flame temperature was 2394 degrees K, and this is for 100%. When I do 400% theoretical air, so for 400% Theo, T is equal to 942 degrees K. So we see there's a big difference between 100%, it's much higher temperature, and lower.